You mentioned that logistic regression is the simplest kind of neural network or artificial neural network. Now we'll look at some more complicated networks. There's this great website called TensorFlow Playground. TensorFlow is a neural network software from Google. So here's what it looks like. We're going to try this data set first, which is called the Gaussian data set. It's got kind of two blobs, a lot like the cancer data set we just looked at. And we can say which properties do we want to feed in? We'll feed in X1, which would be like chemical X, and X2, which would be like chemical Y, or like radius and area, or compactness or something of the cells. And right now, is it doing a good job putting a dividing line between the blue dots and the orange dots, where on one side of the dividing line is mostly orange and the other is mostly blue? It is not doing a good job at all. In fact, the orange area it's highlighting is in mostly for the blue dots, but that's because we haven't trained it yet. You can see it'll have here like what's the loss on the test set and what's the loss on the training set. Um, we can ask it to show the test data as well. So you can see the test data and training data are basically in the same places, which is good. We want them to be fairly similar. So I can, and we've got two things feeding in, and there's kind of an implicit neuron at the very end here. So that would be our logistic regression. So I'm going to hit play and it will train, and we can watch the graph of the test loss and the training loss. And remember, we want loss to be small, so hopefully those will be falling off with time. So I'll hit go here, and they fell right away and are just staying there. And is it doing a good job coming up with kind of a dividing line uh, where the blue is on one side and the orange is on the other? Yeah, I'd say it's doing pretty well. These lines, we can hover over them, and it tells us what the weight on that variable is. A weight of 0.55, weight of 0.59. It's not showing us the bias, but we can see that later. It's still training, but it's pretty much settled on what it's going to be here. So uh, uh, we saw that. So now let's try the circle data set because that's a little bit more interesting. Um, uh, so we can, so now we're trying to separate the blue and the orange still, but they have this different configuration. How well do you think it will do drawing a good line or curve between them if we just feed it these things? Well, let's hit play to run the training. And it seems to have not really come up with a line at all. It seems to be classifying almost everything as orange in the background here. Um, and basically nothing is blue. And it does not seem to be improving at all. When we only have these two inputs, it can only draw a straight line to divide, and there's no single straight line that's better than any other here. Any orientation is roughly equally bad. So it's not surprising that it's not doing a good job. Um, so that was with no hidden layers. Let's go back and add one hidden layer. So that's like neurons in between the inputs and the outputs. Um, oh, so one hidden layer with only one neuron. And we can try retraining. And now we can at least see the dividing line it's trying to draw, but it's really not capturing the idea that one of these is within the other. We can see that the test loss is higher than the training loss. That's fairly typical. Um, and it's just not doing a great job there. So we can stop it. Um, let's add another neuron there. Um, uh, so one hidden layer having two neurons, and we'll start it again. And now it can actually divide the plane into regions like above, middle, and below. But again, for this data set, that just doesn't make any sense. It's got lower test loss and training loss than it did before, but again, it's just not really working there. So we can stop it and we could add another neuron to that hidden layer and retrain. And now it can actually kind of angle one line, another line, and another line to make a sort of triangular region, which you can kind of see happening here. These three, when combined, give us some overlap. It's interesting that this one, the blue is actually on the outside rather than the in, like covering the origin like it is for those and those. But the model is figuring that out and it's applying a negative weight to it, which kind of flips the orange and the blue, while it's applying a positive weight to these two. Also, this little square here is the bias for that neuron. So we're saying we have two inputs. Uh, we have three neurons in a layer and then the final output layer. So it's doing okay. You can see there's still a gap between training and test, um, but it's not really capturing that circular aspect. Uh, but it's, a lot better than two neurons was. Now, if we try four neurons in the hidden layer and train it, initially it still had a band, but now it's doing something more like it kind of has the room to do a square-ish. I guess it's settling more on a triangle. But the numbers aren't all that much better than they were when we only had three. So we've kind of made our model more complicated without getting a lot of return from it, from that extra complication. Um, uh, what if we tried many hidden layers with many neurons? Like we can just bump up the number of hidden layers here, and just we can go with like 7 neurons in each one. I don't have any particular reason for that. So this is giving the model a lot of flexibility. It's like fitting a very high, it's like, but not the same as fitting a very high order polynomial. And we can say, go ahead and train on that. First of all, notice the graph is updating slower because there's many more weights and biases to be adjusting. Um, and the results, the test loss and the training loss are really not that much better. So there's always a trade-off of like, how complicated do I want to make my model? Does it give me a little bit more extra predictive ability, but not much more? Um, you can see we're not even getting a convex kind of region here. There's little concavities to it. That's kind of weird. Um, so that's, seems like a very complicated neural network. The neural networks that we'll use for image processing and for generative AI, like this has dozens or hundreds of weights and biases. AI uses billions of weights and biases. Generative AI uses billions of weights and biases. You can see it's just doing weird stuff. Like it's really stretching to catch that one blue spot here. So it's really kind of overfitting to the training data, but then that one blue spot is, maybe there's one like it in the test data, but there's other stuff out here. So it is just getting just too easily distracted by individual things and not the general circular pattern. Um, some other things to keep in mind. I've shown you logistic regression as a stepping stone, as a way of talking about predictive AI. There are other math models that are not neural networks that could be called predictive AI, such as support vector machines, decision trees, also called CART, classification or regression trees, um, random forests of decision trees. XGBoost still uses decision trees. There's something called naive Bayes. There's something called K nearest neighbor. These were all called machine learning methods before AI broke into the public consciousness so much. These days, people using them might call them AI to make them sound more modern. I've read that XGBoost itself is still often better than neural networks for spreadsheet type data. But XGBoost and a bunch of these others are a different way of thinking that doesn't lead toward understanding generative AI. So I'm not planning on us spending a lot of time with them. Here's some other resources we might use later.